Today we will be discussing solids of revolution and how to determine the volume of those solids. So what I want to cover today is some definitions on what solids of revolution are and their significance in everyday life. And then we're going to talk about some methods to solve for the volume of these solids and then some examples. And then we'll discuss how to choose the correct method for whatever situation you're working on, and then we'll discuss some other resources you can check out. So the question is, what is a solid of revolution? Well, a solid of revolution, if we consider a graph, right, a function on the xy plane, which is what you're very familiar with now, you've taken derivatives and integrals of these all the time. We have a function here. If we were to extrude this or kind of pull it towards ourselves, right, into the z plane, as you will, we would be rotating it kind of around that red line right there, that's that x-axis. And if we do that, we get a shape like this. So it's a 3D object. It's almost like a bulb. And if we go all the way around the x-axis, we get this 3D object by extruding it from the plane. So this is what we consider a solid of revolution. We can do this with all kinds of objects, right? We can use a rectangle and rotate it around an axis, and we get a cylindrical shape. That's kind of more of the basic side of things. If we wanted to go more extreme, we could have on the left like that donut shape right from a circle. Or this like funky shape on the right where we get kind of a cool curvy table look. There's a lot of options here that we can use, but we can use calculus techniques, especially integrals, to actually solve for the volumes of these shapes, which is very interesting. But the real question kind of is, what's the point of doing that, right? Why do we care about this right now? Well, there's a few reasons why. This is actually used in a lot of fields like medical imaging or like MRIs. It's used in engineering and design for different objects all the time, and in manufacturing for like when you're creating washers, screws, kind of things that have some symmetry. These are very useful techniques. It's also a great way to just kind of practice your integral skills, and for many of you, if it's a newly learned topic, it's a good way to kind of get yourself familiar with real applications as to why these integrals are important. And also, in Calc 3, this is actually something you would do all the time, except you have to use different variables. You have to include more, so, x, y, z, you have to include all three of those. In this case, though, we have enough symmetry that we can only use one variable, which makes it very great for Calculus 1 techniques. So how do we actually calculate this volume? Well, we can do it using three different methods, and they're called the shell, washer, and disk method. We'll start with the shell method here. So the shell method, if we take a look at this figure on the left, we have a cross section right there, or like a rectangle. It reminds you of Raymond sums. That's kind of what we're working with here. So what we have here is the delta x is kind of this width of this rectangle, which is defined as the difference between xi and xi minus 1. And we also have a function, y equals f of x, and then f of x star is just kind of like the height we're at for this function, or maybe at the y-intercept. And so what we can do here is if we extrude this rectangle like we did before into the z plane, we would get a nice kind of disk shape. And that is like a 3D shape that we can find the volume of. It will have cylindrical properties, so we can actually use the equation for a cylinder's volume here, which is pi r squared h, as you can see on the top right. So if we use that, we can find the volume of our cross-section using the different notation involved here. And if we do some manipulation on that equation right there, we can actually show the bottom equation is true. And once we get that, we want to get the volume across the entire 3D shape we're going to be doing from some x interval. It could be a to b, as I have there on the bottom. And if we do that, we can do a sum of all of those v's that we've had. But if we want to get the infinitesimal addition, we will switch to integral notation, which is on the bottom there. And so that is our equation for the shell method. So let's do an example of the shell method here. So if we use the shell method to determine the volume of revolution for a given solid rotated around the y-axis, so we're going to be rotating around that green line on the left, we have f of x equals 5x cubed, and x equals 0 and x equals 1 as our x bounds. So let's just go ahead and call those a and b, and then let's plug in our f of x that we're given for the function there. And once we do, we can plot a 10 pi and then evaluate the integral of x to the fourth, and we end up with a value of 2 pi. So, once you get the hang of integrals, this is actually a pretty straightforward process, and it's very, very useful. So the disk method next. So if we use that same idea before, except this time we're going to be taking a rectangle there on the left and extruding it out around the x-axis this time. So in that case, our function is actually going to be kind of our radius, in quote unquote, and then our delta x, or from a to b, is actually going to be our width parameter. So we write the volume equation for the cross section like that, and then if we sum it up again like we did before, we get the integral on the bottom of the screen right there. So let's go ahead and do an example of this one as well. So we're given f of x equals 2 over x squared, and then 1 and 2 are our x bounds. So if we, again, a and b are those values, and then we use our equation we derived before with our function, we end up with a value of 7 pi sixths. Lastly, we have the washer method. So the washer method involves when we have two different functions that we want to find a shape in between them. So if we wrapped both of those shapes around an axis, we would get a new kind of solid. So we want the rectangle or the cross section in between them. So we do kind of what we did before, except we subtract one from the other. And once we sum those volumes from across the entire solid from our intervals, we end up with the equation on the bottom of the screen. So if we use that with an example here, we have f of x equals x squared, g of x equals x, and then x equals 1 and x equals 2. So we use the same kind of process we did before, plugging in our values into the equation we've derived, and then we get 3 pi tenths. So which method do you think you should use? That's the real question. We've made 3 different methods, and we need to decide which one is the most useful for our purposes. So there's this handy little table right here that kind of can help us out. So take a look at this table, maybe pause the video if you need to. If you notice though, right here, it says around the x-axis. So you can actually do this around either the x or the y-axis, or either maybe a straight line. If you want to do x equals 1, you can rotate around that as well. There's possibilities there. If you do that, you do have to manipulate your equations and change your bounds, but if you want, one of the resources I'll show you in a second here can actually tell you how to do that more than this presentation will. But yeah, this is a handy little table to kind of tell you which situations are best for which maybe equations you're given or circumstances. All of them are very great methods though, and I would recommend practicing them all if you have a chance. So if you want to learn more about this, go ahead and go check out Khan Academy's video on this. Khan Academy is a great resource for these kind of things. They have all kinds of different videos about examples and derivations of these volume of revolution. So check that out, definitely. And then also down here, these 4 resources are other ones that I found. A lot of the stuff I talked about today was actually came from these resources, so if you want to learn more from what I pulled for this video, go ahead and check these out. These 2 are from the same website, but they talk about different methods involved. So other than that, thank you for watching.